Have you ever looked at a massive steel ship and just wondered, how in the world does that float? Or how does a 747 stay up in the sky? Well, the answer to all of that is hiding in plain sight. It's in the invisible world of fluid mechanics, the science that governs, well, everything from the air we breathe to the oceans we sail. So, let's dive in and explore these incredible hidden principles together.
So let me ask you something. Think about an airplane soaring through the clouds, a giant hydraulic press that can lift a car with ease, and the crazy, complex patterns of our weather. I mean, on the surface, they seem totally unrelated, right? But believe it or not, they all play by the exact same set of fundamental rules.
And that's the connection, right there, fluid mechanics. It's this amazing branch of physics that's all about how fluids, and we're talking liquids, gases, even plasmas, behave and the forces that act on them. And you know, understanding this stuff isn't just for rocket scientists, it's really the key to understanding how so much of our world actually works.
All right, so here's our game plan for today. First, we're going to get to know the basic character of fluids, what makes them tick. Then, we'll look at the incredible pressures at play when they're just sitting still. After that, we'll see what happens when they actually start moving. And finally, we'll uncover this fascinating property, their built-in resistance to flow.
Okay, so let's start at the very beginning. To really get a grip on any fluid, you first have to understand its core properties. Think of these as the essential building blocks that define everything about how it's going to behave.
First up is something called specific weight. It sounds technical, but it's really simple. It's just how much a certain amount, a certain volume of a fluid weighs. You can see in the formula, it's just its density, that's the little rho symbol, rho, multiplied by g, which is just the acceleration of gravity. And what's really interesting is that this number can change. If you heat the fluid up, its specific weight goes down. But if you put it under more pressure, its specific weight goes up.
Next, we have specific gravity. Now, this is a super useful and simple concept. It's just a plain number, no units, that tells you exactly how dense a fluid is compared to a standard fluid. And for liquids, that standard is pretty much always water. So, if a fluid has a specific gravity of, say, 2, you know it's twice as dense as water. If it's 0.5, it's half as dense. It's just a fantastic, quick and dirty comparison tool.
Now, here's a little point of detail that trips a lot of people up. You might hear the term relative density and think it's the same thing. It's close, but not quite. Specific gravity always compares a fluid to a standard, like water. Relative density, on the other hand, is a broader term. It's when you're comparing a fluid's density to any other fluid. So just remember, specific gravity is a very common, very specific type of relative density.
Okay, so we've got some basic properties down. Now let's move on and see what happens when fluids are just chilling out, not moving at all. This area is called fluid statics, and we're about to tackle one of the most famous principles in all of physics, buoyancy.
And you just can't talk about buoyancy without giving a shout out to the man himself, Archimedes. His principle is the absolute foundation here. It basically says that the upward push, that buoyant force that an object feels in a fluid, is exactly equal to the weight of the fluid it pushes out of the way. It's that invisible force you feel trying to push a beach ball underwater at the pool. That's Archimedes' principle in action.
So, what really makes something float? It boils down to two really simple conditions. First, that upward buoyant force has to perfectly balance the downward pull of the object's own weight. It's a tug of war, and it has to be a tie. Second, both of those forces, the push-up and the pull-down, have to be acting along the same straight line. If they're not, the object is just going to tip over. It's all about a perfect balance.
And all of this leads to a super simple rule of thumb. At the end of the day, it's a battle of densities. If an object is less dense than the fluid it's placed in, it's going to float. If it's denser, it's going to sink. End of story. That's why a giant ship made of steel can float. Sure, steel is dense, but the ship's huge, hollow shape means its overall average density is actually less than the water it's sitting in.
All right, so we've seen what fluids do when they're at rest. Now let's get things moving. This next part is all about fluid kinematics. And what that really means is we're just going to describe how fluids move. We're not going to worry just yet about the forces that are making them move.
So, it turns out there are two classic ways to look at fluid motion. The first is called the Lagrangian approach. This is like putting a GPS tracker on a single car and following its entire journey across a city. You're focused on one particle. The other way is the Eulerian approach. This is like you standing at a busy intersection and just watching all the cars as they pass by. You're observing a fixed point. And while both are useful, for most engineers, that Eulerian view is the one they turn to most often.
For our final section, we're going to dive into one of the most important properties of a moving fluid, and that is its internal resistance to flow. There's a name for this, it's called viscosity. You can just think of it as a fluid's thickness or its stickiness. And trust me, it has huge real-world consequences, from the oil in your car to the pipelines that carry our water.
Viscosity is basically fluid friction. In a liquid, it's all about how much the molecules want to stick to each other. These are called cohesive forces. Just picture how slowly honey drips from a spoon. That's high viscosity. In gases, it's a bit different. It's more about the molecules bouncing off each other. So water, with its low viscosity, flows super easily, while something like honey really resists flowing. This is just so critical for everything, from picking the right motor oil to even predicting how lava will spread from a volcano.
Okay, now here is a really fascinating kind of counterintuitive fact. Temperature affects the viscosity of liquids and gases in completely opposite ways. With liquids, when you heat them up, you weaken those sticky bonds between the molecules so they flow more easily. Their viscosity decreases. Think about how much faster hot syrup pours, right? But with gases, it's a total flip-flop. When you heat them up, the molecules get more energetic, they collide more, and that actually increases their internal friction. It increases their viscosity. So wild. And just when you think you've got it figured out, it gets even weirder. There's a whole category of fluids called non-Newtonian fluids, and their whole deal is that their viscosity changes depending on how much stress you put on them. You've got shear thickening fluids like oobleck, that cornstarch and water mix that get thicker and more solid the harder you hit them. Quicksand is a real-world example of this. And then you have the opposite, shear thinning fluids like ketchup that get runnier the more you shake them.
So there you have it. From a simple idea like density that lets a massive ship float, all the way to a complex property like viscosity that literally dictates how your car's engine runs, these core principles really are the unseen forces that are constantly shaping our world. And that's our look at the fundamentals. But the question I want to leave you with is this. Now that you know about these principles, what unseen fluid forces are you going to start noticing today? Maybe it's the way smoke curls up from a candle, or the way the wind whips around a tall building. Our world is absolutely full of fluid mechanics in action, and now you know what to look for.